Hello, this is ET250 Lecture 14, and today what we're going to cover is just a few examples on these first order differential equation problem, okay? And so the first one we'll do an inductor, an RC one, then we'll do a capacitor, and then the last one will be a big one. That'll be actually a follow-on to the last example we did in the last lecture, okay? So these are kind of warm up, I guess, but the last one, buckle your seatbelts. Okay. So what do we have here? We have an inductor, we have a 6 ohm resistor, a 2 ohm resistor, and a 12 volt voltage source. And what it says is that the switch is closed, all right, and it's in steady state for t less than 0. And at t equals 0, the switch is open. So it starts out closed, and then they want you to solve for I of t, which is this current, not necessarily this one. Now, here's the thing. You're going to have to probably solve for this one anyways, but let's go forth and follow our steps. So in step 1 was identify the boundary conditions, right? So our boundary conditions in this case are going to be when the IL of 0 plus occurs. And we can find that by looking at the IL of 0 minus. And so how do we do that? Well, let's say the switch is closed, t is less than 0, and we're in this steady state situation. And if you recall, for an inductor, in the steady state situation, the inductor behaves like a short, all right? And so if we put a short here, then what happens to this current? Well, the current over here goes to 0. You can even do a current divider, but you have this resistor shorted, no current in this one. All the current coming from here goes into there. Okay, to solve for this, that's actually pretty easy. We can just do an Ohm's law. Now, if you're doing an Ohm's law on this, be very careful. KVL first, so you have a plus or minus 12, and then Ohm's law. Or you can do a nodal Ohm's law where IL equals 12 minus 0 over 2. Okay? All right, so Ohm's law here will be 12 over 2, which is positive 6 amps, and then I here is 0. Okay, so what that says is the IL of 0 minus before the switch opens is 6, and the I here of 0 minus is 0. Now, how does that help us? How does the information before the switch opening help us? Well, this one actually doesn't, but this one for IL, it does because there's that inductor transition condition. The inductor, due to the flywheel physical nature of the inductor, the current cannot instantaneously jump, and therefore the current at 0 minus equals 0 plus, and it's 6 amps. So this is going to be our useful boundary condition. Okay. Now, with that boundary condition, we can think about how an intuitive plot is created. Now, the other thing we could think about is, well, what's the current going to look like once this switch has opened and we're at steady state again? Well, once this switch opens, we're only going to have these two elements, the resistor and the inductor, and it's going to try to maintain that 6 amps. But then after a while, it'll dissipate all its energy and spool down. Okay, so the current's going to stay at 6 and then spool down to 0. So what we're expecting to see is something like this. IL is going to be 6 and then it spools down. Okay. Okay, well, what about the current? Well, once the switch is open, this guy goes away, and these currents are the same but opposite in sign by KCL. And so you can see that immediately this I, which was 0, is going to jump to negative of this. So it's going to go to negative 6 and spool down as well. So it'll jump to negative 6 here. Okay, so this is what we should see for our e to the st kind of equations, right? Okay, and so I bet you we're going to see something like this. IL is equal to some 6 e to the minus st plus 0 amps. So I bet you K2 is going to be 0, K1 is going to be 6, and S will be related to R and L, okay? All right, so let's go and start crunching and see if we get this intuitive result from the math. All right, so what we do is we now open the switch. Okay, we open the switch and we apply our KVL, KCL Ohm's law. We can follow those steps that I had outlined from the previous lecture. Okay, so we got step 1 done, we got step 2 done. Now it's step 3. We're in the transient condition here, and this is essentially gone. And I put in a nice label for the voltage. I have my IL, I have an I, and I put a dummy VR polarity and voltage, right? So make sure you're doing this. If you're going to apply these voltages and these rules and laws, put your polarity, put your current direction, and give it a name. Okay, so that's closed off. or sorry, opened off, right? And we can see by KCL, I equals minus IL, we can write our Ohm's law, and we can write our inductor equation, right? VL equals positive L DIL in this case, and Ohm's law VR equals IR. Okay, good. The other one we note is that VL and VR are the same by KVL. So this is all the circuit stuff. And we can start smashing everything together and get ourselves our first order differential equation. So VR becomes IR, VL becomes LDILET, and then I'm going to make this KCL substitution, and I'm going to have negative IL for I. Now notice when I see this first order differential equation, I want the same variable to be the non-derivative and derivative version. So I wouldn't want to mix I and IL. And I think I emphasized that in the last example, and we'll see it again in today's last example. Okay, once we get the first order differential equation, the next step is the guess. We know that IL is probably going to be like this. It's going to have some K1S and K2 in it, just like here. Boom. And we know the derivative of that is this, SK1 e to the ST. We're going to punch these in, and then the next step is solve for the K1, K2, and S using the information given. And remember, when you plug these in, you're going to have two sneaky equations, even though you see one, all the terms attached to the E to the ST and all the terms that are not attached to the E to the ST. So let's go ahead and do that. So when I plug this in, let's see what I get. I get negative K1 e to the ST plus K2, that's the IL, times R, equals L times SK1 e to the ST. Okay, not too bad. And I identify e to the ST, e to the ST, good. So minus K1R, good, and LSK1, excellent. This allows me to solve for S eventually, but let's do the other one. Minus K2R, don't forget that minus. In this case, I think it doesn't matter. And what I see is S is negative R over L. Good. Okay, so that's actually going to be this one, negative R for L over L for S. Okay. I should actually make that positive. Positive S, negative R over L. Yes. And so this actually ends up being -3. What is K2? That ends up being 0. Fantastic. We're almost done. We still got to solve for K1. We think it's going to be 6, but let's just confirm for sure. We look at our boundary conditions. IL of 0 plus is 6. If we plug a 0 into our answer, 0 and 6 here, sure enough, K1 has to be 6. Boom. And that's it. And look, this equation that we got matches our predicted equation, and this will actually plot out the same plot that we expected, where the current starts at 6 and spools down. So this is what your IL should look like. Now by KCL, I is equal to negative IL, and don't forget that that I is this one over here. And so we get a -6. And so hopefully this matches our intuitive plot, okay? Not too bad. So I hope you're seeing this first order differential equation. Might seem scary at first, but it's not too bad as long as you've done a bunch of these problems and you start really clicking in the intuition. Okay, let's do another problem. So this problem is a capacitor one now. Okay, so what do we have here? We have the capacitor. They've given us a bunch of values, 50 for this voltage supply, 1 mega ohm, okay, and then 2 microfarads. What did they say about this switch? If the switch has been open for a long time, so when you hear a long time, that means it's reached steady state, before t equals 0, find V as C of t after the switch closed, okay? And let's think about the situation. So the switch is open and then it closes. So when the switch is open, you have a voltage supply, a resistor, and capacitor. Well, we've seen this before. This voltage supply is going to make sure that this capacitor is charged up. And in the steady state, this is going to behave like an open. So this is going to have no current flowing, and this voltage across this capacitor will be the same as this one, 50 volts in this case. Okay. Now let's think about what happens when I close the switch. When I close the switch, what's going to happen? Well, when I close the switch, the current's going to dump into this resistor, this R2, and eventually it'll reach steady state again. In steady state, this will be again an open circuit, but now VC will be across R2, and it'll be, I think, a smaller number because you're going to have a voltage divider situation. It's as if this is not there, and now VC will be R2 over R1 plus R2 times VS. Okay, so let's do, so the question asks, please sketch VC from -2 to 5 seconds. No problem. That's easy. Determine the time constant. No problem. Okay, time constant is RC. Okay, so let's go ahead and follow this analysis. So when we're in steady state and the switch is open, I is 0, good. And by KVL, good. VC and VS are the same, 50 volts. Yep, that's what we stated. When the switch is closed and we're back at steady state, then we can see that VC is this, yep, and we have a voltage divider. Good, that's exactly what we had just stated. So it'd be 25. So you're gonna start at 50, you're gonna close the switch, and it's gonna spool down to 25 volts. And so this would be our intuitive plot. Start at 50 and spool down to 25. Not too bad. And so we could then go ahead and follow our first order transient differential process, blah, 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 to get the equation that matches that. So what we do now is close the switch. Okay, we close the switch. So we have this situation now with the switch closed, and then apply our KVL and KCL and Ohm's law and all that good stuff and our new capacitor equation. So in this case, what is it? Well, we got to be careful. We got I going into the positive terminal. So the positive I equals C dV C dt. Good. What else do we have? We have maybe a nodal Ohm's law. And by coincidence, if we put a ground here, this node is VC. So this I1 is VS minus VC over R1. And this nodal Ohm's law here is VC minus 0 over R2 for that current. Good. That's what I have here. And if I put everything together, this current, this current, this current, I can use KCL. So I1 equals the sum of these two. Bang. Okay. Now I have all this stuff. This is my circuit stuff done. That was it. Sometimes it's easier like this. Sometimes it's harder, as you'll see in the next the next example. It's actually a little tricky. Okay, so now I can start plugging everything in. I can plug in this for I1, this for I2, and this for I. So what do I get? I get VS minus VC over R1 equals I2, which is VC over R2, plus I, which is C dVC dt. Great. And now this is just algebra. I'm like, okay, well, R1 and R2 multiply the entire equation so that I get kind of rid of these guys, and I get this. R2 VS, because the R1s cancel here, minus R2 VC, good, equals, I multiply this, R1 VC, good, plus R1 R2, R1 R2 C dVC dt. And then I can bring, the VCs the other side, just start combining like terms. But at the end of the day, even at this point here, it's a first order differential equation. This is great. VC and dVC dt, they're all there. Excellent. And all the other variables are things we know, R1, R2, and VS, which are right here. Okay, we know the next step. The next step is write our guess and plug it in, right? So at this point, I hope it's getting a little repetitive, okay? Okay, so we can write our guess for our non-derivative and derivative and plug it in here. So we're going to get R2 VS equals R1 plus R2 times this K1 e to the ST plus K2. Good. And then plus R1 R2C times the derivative. R1 R2C times the derivative. Excellent. Again, we go, well, what do we need to do? We need to separate out. So we have the e to the st and the non-e to the st. So with the e to the st terms, we look at this, we got R1 plus R2 K1. We have R1 R2 C SK1. And this equals anything? No, equals 0. Great. So if I look closely here, it looks like the K1s cancel. I get S equals negative. I got to be careful. I get negative R1, R2, or R1 plus R2 on the other side, divided by this guy, R1, R2C. Okay, not too bad. If I look at all the terms without e to the st, I get R2 VS, good, equals to K2 times R1 plus R2, good. And so here I actually get a non-zero K2 because K2 is R2 VS over R1 plus R2. I bet you this is related to the 25, I think. Okay. The last thing I got to do is use my boundary conditions, right? I got my S, I got my K2, I now need my K1. Okay, that K1 is probably related to the 50. And so I have, at time 0, I have 50 volts. So I plug this in and I go, okay, well, I can put a 0 here. I got a 50, right? Oh, but I had a non-zero K2. Good, I can plug everything in. Great. And I know that K1 is 50 minus this guy. And if I plug in all the numbers, I get, well, this is all the algebra, all the symbolic version, right? I get actually 25 for K1. Okay, and it actually ends up being 25 for K2. Okay, so let's do that a little bit slowly, right? Let's go back up here. So K2 is this one, and I'll even pull out my calculator. Let's just make sure that we have everything right. So K2 is this one here, and let's take our numbers. So what do we have? 1 mega ohm, 1 mega ohm, 50 volts. So, well, this is 1 mega ohm divided by 2 mega ohms. So that's actually, the mega ohms cancel. I'm left with 1/2. So 1/2 times Vs, 50. Oh, that's 25. I don't have to punch that in my calculator. That's 25. Easy. Okay, so this is 25. And then if I know that this is 25, well, K1 is 50 minus that. So that's also 25. All right, well, so much for the calculator. Okay, so yeah, I'm happy with this, 25 and 25. Now, what about the S term? Okay, so the S term in here, what is this? This is this guy. So the S is 1 mega ohm plus 1 mega ohm. Okay, that's 2 mega ohms divided by 1 mega ohm times 1 mega ohm. That's a mega ohm squared. So I have a mega ohm and a mega ohm squared. Interesting. So I have 2 mega ohms over a mega ohm squared times the 2 microfarads, right? Okay, what is that? So it looks like the 2's cancel. Is that correct? So I'm left with a, well, this cancels here. So I'm left with 1 over mega and micro. Doesn't that cancel? Isn't that 10 to the 6 and 10 to the minus 6? I think that is. So does that mean my S equals -1? Okay, I think so. Very good. So -1, what a coincidence. Nice. Okay, that means our time constant for this one is actually 1, our time constant, because remember the time constant is the time such that e to the -1. Well, if the time is 1 second, you're still going to get, 1 in here. Great. Okay, because we have e to the minus t. The time to get a 1 in here is 1. Nice. Nice. Okay. And don't forget our time constant is also r times c, right? The r times c. In this case, the r is like this this, what do you call it? R1, this r equivalent is r1 plus r2 over r1 r2, right? Okay. I think this is a better way to think about it because you're always going to get this right. If you just remember time constant is rc and you look at this system, you're like, well, which r? Is it that R? Is it that R? Which one? Okay. And so I hope you guys can see, well, it's this R1 plus R2 over R1 plus R1 times R2 in this case. Okay. All right. Now, if I were to plot this, I would get this decaying plot. And you can even test at 0, what do I get? E to the 0 is 1, 25 plus 25, good, starts at 50. And as e goes infinity, this goes to 0, so I'm left with 25, and I get a decay from 50 to 25, right? And I could even plot what happens, what is, let's say they want it at 5 seconds, I could even find out what this is. So I could say, what is e to the 5, right? I actually say -5, okay? And then I can say times 25 plus 25. Well, that's silly. I need to times 25 plus 25. My calculator requires me to put a decimal point. So it's 25.16 volts. So maybe I can put that in here. At 5 seconds, then it's 25.168 volts. Not too exciting. It seems like you've nearly settled out, and that should make sense. At 5 seconds, that's the equivalent of 5 time constants. At 5 time constants, you can see that we're nearly there, and this proves that we are. Okay, what about at 1 time constant? Well, that's 1 second. Okay, that's 34.197 volts. So let's see, what is this? 1, 2, 3, 4. So at 1 second, so that's about here. So that's 34.197 volts. Okay, and that makes sense. We're 63% of the within of the final value. Yeah. Okay. Good. All right. So this is good. I hope this again solidifies this first order transient process. Okay. So now let's go to this crazy problem again. We saw this crazy problem last lecture, but let's revisit it. I'll walk through it again, and then we're going to do the continuation. So what was the problem? The problem was we have a inductor, an RL system, and in that RL system, we started out with the switch initially closed, if you recall. The switch is closed here, good, and everything's in steady state, great, and this inductor is behaving like a short. Remember, inductor behaves like a short in steady state, capacitor behaves like an open in steady state. Okay, so it's short, and we had this situation where R2 and R3 are in parallel, and so we had a nice current divider system, and I believe the current here was 2 amps, this was 1 amp, that was 3 amps. Okay, and so you can review the previous lecture and see, but it's also right here if you want to pause the video and take a look. But what we did was we analyzed it with this. I know it looks kind of crazy, but we analyzed in steady state, just these two resistors, current divider, squashed the resistors together, solved for the total current, brought that total current in, solved for the current divider again, got the 2 amps. KCL tells me if that's 3 and that's 2, well, that's 1, easy, okay? And we use the transition condition to show us that if IL of 0 minus is 2, well, IL of 0 plus is 2. So the current in the inductor can't jump, even though the current here in R3 can. Okay, good. So we had that situation going, and then we analyzed it when the switch opened, and what was happening was this was 2 amps, and then just like the first problem, it spools down once that switch is open. Okay, so it spools down, so we should see a current in this inductor that starts at 2 and spools down. And then if you recall, the current in here due to KCL is opposite of this one, similar to the very first problem we went over. And so it started out as 1 amp right here and jumps to -2 and spools back to 0. Okay, so these are opposite. The voltage in the inductor, what does it do? It starts at a 0 because we're at steady state. And then it acts like an upside down battery to maintain the party, right? It wants to keep that current flowing. So think of it as like a positive voltage down here, pushing current through here. So it jumps negative and spools back to 0. We followed that first order transient process. Okay, what was it? Well, we did KVL and Ohm's law and the inductor equation. And we got the first order differential equation. We made sure it was in terms of IL and not I. We had the IL and DIL. We plug it in, put it in here, get the e to the st and non-e to the st terms to solve for S and K2, apply our boundary conditions, solve for K1, yada, yada, yada. We have our answer, this one, okay? When we plug in all the numbers, we get IL equals 2e to the minus 45t, which matches this, great. And because I equals negative IL, we get this. If we want to get our voltage, then the voltage is the derivative of this times L, no problem. On the last YouTube video, I made a mistake. So this should be -90, that is correct, but this actually became -180 because the L was 0.2 and not 2. So we get -18, not -180, okay? So again, this is -18 and not 180, and you can see it jumps to -18 and then goes to 0. Okay, now that we've reviewed that problem, and we can go back to this new problem. So let's continue. So let's say we are at a situation where, yeah, we're here, we've opened the switch, but now we close it again, okay? So we have our same system. So I just rewrote those equations that we just derived here, right? The IL and I and VL. And now let's say it's spooling down, right? This current is winding down, and now before it can steady out, we're saying, close it again, right? So bring the voltage supply back, right? And so what we can do is we can compute what is IL and I and VL using this equation right before 0.01 seconds occurs, okay? And we want to plot everything. It's the same values. We're not changing any of the values. And let's see what happens. Okay, now we can, again, follow our steps. Boundary conditions. Now this time it's not 0 minus and 0 plus. It's 0.01 seconds when the switch occurs, okay? And so we can, again, still use our transition conditions. We don't care about 0 plus, 0 minus. We care about 0.01 plus and 0.01 minus, right? So be careful. All right. Then what we can do is go, all right, well, what is the minus value? Well, we use our equation that we got from the last one and go, okay, IL of 0.01 minus, which is valid for this one, is 2e to the minus 45 times 0.01, which is, when we compute this in our calculator, 1.275 amps. So that's IL. Okay, great. What about I of 0.01 minus? Well, it's just the negative of this. Okay, so that's just negative 1.275 amps. Great. And what about the voltage? Well, we just put in a 0.01 here and we get negative 11. So that means that this point here at 0.01 seconds, whatever happens to be, is negative 11.47 volts. Good. And what about over here? At 0.01 seconds, it's 1.2 amps. Okay, so it's around, that makes sense. And then here, it's negative 1.2 amps. Okay, good. Always double check that your numbers that you're getting make physical sense, right? Don't move on until things make physical sense. All right. So what about at time goes to infinity? Well, at time goes, I have this switch closed. At time goes infinity, this again behaves like a short. We already did that problem. We already solved for those currents. And those currents, if you recall, are 2, 1. This is 2 amps, this is 1 amp, and this is 3 amps. When the switch is closed and it goes back to steady state for a long time, and this voltage go to 0. We've solved this already. That's nice. So we can make some intuitive plots. The current is going to start at 2 initially. So this is closed. It's going to start at 2. I open it. It's going to start decaying off. This current's going to start decaying off, and then I'm going to close it again, and this current's going to come back up to 2. Should make sense. Okay, what about this current here? This current here, I have it closed, steady state. It's going to be 1. I open it. It's immediately the negative of IL. Okay, so it does this. And then I close it again. And this is kind of an interesting thing. This is kind of hard to build the intuition as to why it does this, but it's going to jump greater than what the steady state would be. Because imagine this is, the current can go both ways. You can see here that this current in the inductor path has not achieved its full potential. So how do we make up the slack? You get a little more current in this R3 branch. That's a little tricky to get, but hopefully the math will show us that this is true. It starts actually higher than 1 after you've closed the switch back again and then decays back to 1. Interesting. Okay, so this is where the math can give us some more intuition. And then finally, the voltage, what's the voltage going to do? Well, when it's closed, it starts at 0. When I open it, it jumps to negative. And then when I close it again, we're trying now force current back the other way. It's going to prop up the other way positive and fight that again, the initial change. So you're going to get this jumpy behavior, negative bang, positive bang, and then decay to 0. Okay, so this is our intuitive plot. And now what we're going to do is we're going to go through this hairy analysis to find the first order differential equation, solve for IL, I, and VL. Okay. All right. So this is, by the way, this is VL of T. Okay. I of T and IL of T. Good. Okay. So this time when we solve it, it's not going to be as clean because now we have the voltage source in the R1. When the previous part, we only had these 3 terms. So this is going to be a little bit of a hairy mess, but it's not that bad. Okay. So what do we got here? Switch is closed again. R1, R3, IL, VL, R2, VS. Okay, we got everything. And notice I did myself a favor. I put a little node voltage here and a ground. Now we don't know what this node voltage is. We only know VS, which is 12 volts. And then this is what, 2 ohms and 3 ohms, 3 ohms and 6 ohms, right? And then this is 0.2 Henry. So we don't know what this voltage is. It's a dummy voltage. We also don't know what this current is. It's kind of a dummy current. Okay, we want to know IL, we want to know I. So our intention is to get a first order differential equation with either all IL or all I. Okay, let's do it. So we can start chipping away at this with our basic. So we're at step 3, I think. So IS equals I plus IL, KCL, we're going to apply our KCL, KVLs, Ohm's laws, all that stuff in our new inductor equation. Let's apply some nodal Ohm's laws. We have 3 resistors, in fact. So we have Vn minus 0 over R3, Vs minus Vn over R1, that's Is, and we have Vn minus VL over R2. Good. Okay. I'm going to hold that later. And then we have our inductor equation, VL equals L, positive L di L dt. Good. Okay, I can plug these into the KCL here, so ignore that. And I get Vs minus Vn over R1, good. I get Vn over R3, good. That's from this one. And IL is, I'm just going to leave IL. I'm not going to actually plug this in. You'll see why. You'll see why. So if I look at this equation, I don't quite have my differential equation that I want. I have IL, but then I have Vn. Vn is my unknown guy. Remember, it's my dummy variable. Vs, R1, R3, that's good. but Vn is a little annoying here. But do I have enough information in these guys to be able to pull in my DILT? Notice I haven't used my inductor equation yet. If I look at this one carefully, this is where a little bit of your of solving a bunch of month one, midterm one problems is going to help, because you can start to see some of this. Otherwise, you start kind of getting, chasing your tail. If I look at this one, look at how I can solve for Vn in terms of IL and VL, right? Vn equals ILR2 plus VL. You can see that? Okay, that's a good thing. I have an IL and a VL there. And let's say we want to get rid of VL. Oh, nice. I got L equals DILTT. Okay, that's nice. Vn equals IL R2 plus LDILDT. And that guy goes into here. Now what I have is a nice equation with only IL and its derivative in it. No I, no VL, no Vn, right? And let's look closely. Vn minus IL R2 plus LDILDT, good, over R1, good, equals Vn, which is, again, IL R2 plus LDILDT over R3 plus IL. Good, this is my first order difference equation. Like I said, this problem is a little bit hairier because you have all this stuff in here. Okay? So we know what to do with that. We can solve for K1, K2, and S because we know IL is going to be that special E to the ST form. Okay, so we're going to plug in our guess, and we're going to do this. And I know it looks nasty. Let's just do it one variable at a time. So Vs divided by R1, good, minus, now let's be careful here, IL, which is K1 e to the ST plus K2, okay, K1 e to the ST plus K2, all right, good. What else do I have? I have minus L over R1 times SK1 e to the ST. Good. Okay. And then what do I have? Oh, don't forget, that's R2. That's why I pulled out the R2. And then I have equals to IL, which is K1 e to the ST plus K2 times R2 over R3. Good. Plus L over R3 times SK1 e to the ST plus IL, which is K1 e to the ST plus K2. Whew. That's a lot. I wasn't lying when I said this was a hairy problem, right? Okay. The process is still the same. It's just we got to be a little bit more careful on the bookkeeping here. Okay. So we just got to be very precise and confident with our steps. Oh, and you know what? Why don't we just do one more check just to make sure? When you get to these equations, you don't want to just blindly do it. And so Vs over R1, good, minus R2 over R1, IL, K1 e to the ST, good, plus K2, good, that's one, yep. And then let's go here, minus, good, I get that, minus L over R1, good, SK1 e to the ST, yep, I'm happy with that, equals to K1 e to the ST, yep, times R2 over R3, great, plus L over R3, SK1 e to the ST, yay, plus K1 e to the ST plus K2, good, okay. Whew, it's a lot. That's a lot. So now we go, well, what about the terms with and without EDST? Again, we got to be careful. So the first term is minus R2 over R1 K1, good, minus LSK1 over R1, good, equals to R2 over R3 K1, good, plus L over R3 SK1, good, plus K1. Oh my gosh, that's a lot, but that's it. And if I look at this, can I solve for an S? Well, I can cancel all the K1s, good. I can combine the S, so I get S over here. That's a positive L over R1 and L over R3. And I can bring this over here. And I can, don't make this mistake. This is a 1, right? Once it cancels out. So it comes over 2. So I have a minus R2 over R1 minus, minus this one, R2 over R3 and negative 1. I can imagine a lot of students would make that mistake, but hopefully not you watching this video. Okay, so then this S is here minus this guy here divided by this one. And I just pulled out the minus so that all this is positive. Ooh, that's a crazy looking exponential term, right? Okay, it is what it is. Okay, what about the next one? All the terms without e to the st. So I have Vs over R1, good. I have negative R2 over R1 K2, good, equals to R2 over R3 K2, good, and K2, good. If I look at this one, I can combine all the K2 terms. So I get R2 over R1 positive, R2 over R3 plus 1, and I get Vs over R1 good, and then I get K2 equals this divided by this mess, right? Okay, or 1 over this mess. Oh, nuts. And then the last thing we have is the boundary conditions. Well, we saw for the boundary conditions, one of them, it was the current IL at 0.01 seconds, okay? Oh, before I did that, apparently on my solution, I just punched in the numbers, right? So let's just make sure, we'll go back and make sure my solution has done this correctly. If these are the numbers here, R2 is 3, R1 is 2, good, plus R2 is 3, R3 is 6, good, plus 1, times inductance 0.2, good, and then I get 1 over R1, 2, plus 1 over R3, 1, 6, good. So if I punch that in, I get negative 22.5. And then over here, I get 12 over 2, R1 is 2, good, and then 1 over 3 halves plus 3, 6 plus 1. Okay, good. So that means my K2 is 2 and my S is negative 22.5. All right. The boundary condition we already found was IL of 0.01 is 1.275 amps. So here's how we apply it. I have my IL equals K1 e to the minus 22.5 plus 2. I'm going to put the 0.01 here for this time, and I'm going to put the 1.275 over there. Okay, that's how you apply it. Now I have one equation, one unknown. This is a number I can punch into the calculator, and I can solve for K1, right? So 1.25 minus 2 divided by this is going to be negative 0.9079. That's my K1. And my final IL result is negative 0.9079 e to the minus 22.5t plus 2. Okay. So what does that mean for my VL? Well, VL, if you recall, is L DIL dt. Okay, L is 0.2, DIL dt, that's pretty easy. Negative 22.5 times this thing without the constant, good. And so if I crunch all these numbers together, I get 4.085, 7 equal, is that a 7? E to the minus 22.5t. And then what about for the current? That is an interesting one. We can go back to our analysis here. This is tricky, right? This is tricky. We know I is Vn over R3 because of a nodal Ohm's law, right? And we also know that Vn, as we said before, equals IL R2 plus VL, right? And so that's this one. Okay, so instead of doing another first order differential equation, we just pull out from our step 3 and solve for I. Well, we have an expression for IL as this. We have an expression for VL as this. And we can put it in. So R2, which is 3, times this IL term here, negative 9 e to the minus 22.5t plus 2, plus VL, which is this guy, divided by R3, which is 6. Okay. Now we can start crunching everything. All the terms with e to the st ends up being 0.226. And then look at this, 3 times 2 is 6 over 6. That's 1. So this is the equation for I. Kind of nutty, kind of hairy, but makes sense, okay? We can even calculate for the plus terms, what would the VL, the new VL and the new I be at 0.01 plus? So we can put a 0.01 here, and we get 3.26 volts here, and we get 1.18 volts here. Notice that this is greater than 1. And what's our new time constant? New time constant is 1 over 22.5, right? 1 over this number, which is 0.04 seconds. So if we compare it to the previous one, the previous time constant was 1 over 45, which is 0.022 seconds. We get double the time constant. It's slower. So when we close it again, we actually are going to see a slower response. So if we were to plot this, what would we get? We would get, just like our intuitive plot shows, the current goes down now, and now we can actually punch in numbers, but we get it goes down to 1.275. That's the number it achieves when I decide to switch it closed again, and we rise back up. And this part will be a slower rise time than this first part, okay? And so, by the way, what is this? This is, in this time is less than 0, switch is closed, switch is open, switch is closed again. So switch closed. And here the switch is open. And here the switch is closed, right? Okay, this was the first problem. This is our new problem. Okay, what about the current? Current is happily at 1. It opens the switch, jumps to -2, and then we close the switch again, jumps to 1.18, and then decays back to 1 amp. Okay. And the last one, the voltage, what does it do? Jumps to -18, okay, goes to -11, and then jumps up to 3.26 and then decays to 0. So hopefully this matches, yep, matches our intuitive plot. Yes, victory. Okay, let's switch over to the simulation and see if we get the same response. So we're going to switch over here, okay, and we're going to check this out. So here we go. We have our simulation. We're looking at it, and I'm going to run this now, and we can see that this is pretty much in steady state. Okay, I have 2 amps of current in the inductor. I have 1 amp of current in this 6 ohm resistor. And what I can do, I'm going to try my best to open it and close it, right? For to simulate what we have. Open it and close it. Okay. Did I do a decent job? Let's check. I'm going to let it run for a bit. Okay. So check this out. If I look at this plot properties, each division is 10 milliseconds, which is 0.01 seconds. Oh my God, pretty darn close, ladies and gentlemen. Look at that. One division is 0.01 seconds. I was pretty close. So you can see here, this current in this inductor is happily going along at 2 amps. It decays down, just like we predicted. And then look, it goes back up once I close the switch again and settles back out to 2. And notice the time constant, it's slower. Yes, it's slower. Okay. All right, look at the voltage. The voltage goes here at 0, drops down to nearly -18, goes up to nearly 11. Look at that, I was pretty close, -12, right? And then jumps up to about 3, yep, 2.73, and then decays to 0. Yes. Okay, what about the current in the resistor? The current in the resistor starts at 1, jumps down to -2, right? And then comes back up, -1, and then goes up to above 1 point something, and then decays back to 0. Yes. So this is showing exactly what we predicted in our first order differential equation process. Nice, nice. And so we can run this. And if I kind of switch this back and forth, you should see the sawtooth-like behavior in the current, right? And then you'll see the steppy behavior in the voltage. All right. Well, again, the link for this simulation will be in the description of this video. You can play with this to make sure that everything is intuitive and matches your understanding. And thank you for paying attention. Have a great day.